we're going to talk about separable differential equations, and we hadn't had an initial condition up to this point. So this is the first problem where we do have an initial condition. Our first order of business is just to get the variables separated. So all the x's on one side, all the y's on the other. And they already have like the dy dx separated into two parts. So I'm just going to subtract that term, move it over to the other side. So we'd have 1 plus x to the fourth dy equals negative x times 1 plus 4y squared dx. And then I'm going to divide both sides by 1 plus x to the 4 and 1 plus 4y squared. So I'd get 1 over 1 plus 4y squared dy equals negative x over 1 plus x to the fourth dx. So now we have all the y's on one side, all the x's on the other. So we're ready to integrate on each side. And so let's think about the left-hand side first, the side with y's. What is that going to involve? Okay, yeah. If we had a y in the numerator, it would be a u substitution and then natural log. But since there's nothing, if we let u equal 1 plus 4y squared, our du would be 8y dy, and we don't have that 8y dy. So this is more like a 1 over 1 plus, I'll say, w squared, right? So if you want, you could make a u substitution, but you just let u equal 2y. Now, you don't have to do this, but say we did. U equals 2y, then du would equal 2 dy, or 1/2 du equals dy. And then the left-hand side would be 1 over 1 plus u squared, and then the dy is 1/2 du, and I'll bring the 1/2 out in front. And then that's where we are getting arctan. So that'll be 1/2 arctan u. I'll worry about what's on the right-hand side in a minute. But this is 1/2 arctan u, and then I'm going to do the plus c on the other side. And then we would substitute back in for u. So 1/2 arctan 2y. Okay. Now let's go back to the right-hand side, the side with all the x's. How are we going to do that? Or what do you think that one's going to involve?
Substitution of x squared.
Yeah, so this is also going to be, it's going to turn into an arctan problem. So we would I'll say w equal x squared, then dw equals 2x dx. We have x dx left over. So I'm just going to multiply both sides by 1/2. dw equals x dx. I'll bring the negative out, just all the way out in front. So we would have negative the integral x dx is being replaced by 1/2 dw. I'm actually going to bring that 1/2 all the way out in front. So I'm just going to use that negative sign, make it a little bigger, fraction bar, negative 1/2. And then I would have 1 over 1 plus w squared dw. So we get negative 1/2 arctan w. And then here's where I'm going to do my plus c. And then substitute back in for w. And then I would probably multiply both sides by 2. So I just get arctan 2y equals negative arctan x squared. Now, if you want to put plus 2c, that's fine. I'm just going to let my constant kind of absorb the 2. If it was an arbitrary constant and I multiply by 2, it's still an arbitrary constant. If you want to call it 2c, if you want to call it k because it's different, that's fine. I'm just saying there's some arbitrary constant there. But now we are given an initial condition, y of 1 equals 0. That's going to help us solve for c. So if we have y of 1 equals 0, then 1 is going in for x and 0 is going in for y. So we'd have arctan 2 times 0 equals negative arctan 1 plus c. What is arctan of 0? 0. What is arctan of, what is arctan of 1? Pi over 4. So just add pi over 4 to both sides. So c equals pi over 4. So then the implicit solution bless you, is arctan 2y equals negative arctan x squared plus pi over 4. And this is fine. You could solve for y by taking the tangent of both sides, tan of arctan. You're just going to get the 2y. But on the right-hand side, you'd have to use a trig identity, like the tan a plus b, whatever that. I don't have that one memorized, but you could look it up and simplify it. You could get an explicit solution, but I'm fine with this. Okay, and then an example from the text. So it says solve this initial value problem. So dy dx equals y squared minus 4, and the initial condition is y of 0 equals negative 2. And it says, notice that this is an autonomous differential equation, which is what we covered in 2.1, where dy dx was only a function of y, and we found the critical points, and then we saw whether that was an attractor, repeller, or semi-stable. So it's the same idea here, but if we're trying to solve it, like there we were just drawing what the solution curves look like without actually coming up with a solution. Here we want to actually find the solution. Okay, so it's separable. So I just divided both sides by y squared minus 4 and multiplied by dx. And then using partial fractions, like this, a U substitution doesn't work, and this is not arctan. Arctan goes with plus. So you could either do like a trig substitution where y equals 2 sine theta, and then, 2 secant theta when the variable squared minus the constant. But then you'd have to switch everything to trig functions. Whereas I would think partial fractions would be much easier than doing the trig substitutions. And then you'd call y squared minus 4, y plus 4, y minus 4. So then you can split it up into 2 fractions, each factor of the denominator. You can create a fraction with that. So it'd be like a over y plus 2 plus b over y minus 2, and then you'd solve for the a and the b. We'll see that later in the semester, but that's a Calc 2 topic. So integrating then both sides of this and using partial fractions, if you solve for a and b, you'd get negative 1/4 and positive 1/4. And then on the other side, you're just integrating dx or 1 dx. So it says complete the problem. Okay, so the first term, so the negative 1/4 is a constant that comes out in front. And then what about the antiderivative of 1 over y plus 2?
Log of y plus 2.
ln. Now, I am going to use absolute values. And then plus 1/4 ln absolute value y minus 2 equals, and so what do we get on the right-hand side? X. And I'm going to do my plus c on this side. So the first thing I would do is multiply both sides by 4 to clear fractions over here. So I'd get negative ln y plus 2 plus ln y minus 2 equals 4x, and then I'm just going to still say plus c. It's an arbitrary constant. 4 times that arbitrary constant is also an arbitrary constant. And then we can use properties of logarithms. ln a minus ln b is ln of a over b. So I'm going to use that property right here. And so we'd get the natural log, the positive one is y minus 2 over the negative one is y plus 2 equals 4x plus c. And then we could exponentiate both sides to get rid of the natural log. This technically right here is an implicit solution, which is okay. I'm just going to work through to the explicit solution in this example. So I'm going to do e to both sides. And so e and ln, they are inverses of one another. So I just get y minus 2 over y plus 2 equals e to the 4x plus c. And this will come back quite a bit in later sections, that e to the 4x plus c. What you want to do is use the law of exponents kind of in reverse. I want to write this as e to the 4x times e to the c. That's like the addition property for exponents in reverse. If you have the common base, multiply together, you add exponents. And then e is a constant, c is a constant, so this whole thing is a constant. I'm going to call it a k this time. So I'd have absolute value y minus 2 over y plus 2 equals k e to the 4x. Bless you. Our initial condition, I'm going to keep going, but let's just look at our initial condition right now. It was y of 0 equals negative 2, which means we're going to plug 0 in for x and negative 2 in for y. Well, what about that? It's undefined when y is negative 2, right? So I'm still going to follow through with this, though. So y minus 2, y plus 2, k e to the 4x. I'm going to ignore absolute values for a moment and see how we could go about this. It's with absolute value, you can't apply the distributive property. So I just want to show you how you would do it if you didn't have to worry about the absolute values. So here, suppose I have y minus 2 over y plus 2 equals k e to the 4x, and then multiply both sides by y plus 2. And then distribute the k e to the 4x. That's what we can't do with absolute values. So I'd have k y e to the 4x plus 2k e to the 4x. So if I want to solve for y, I want the y's on the same side. So I'm going to subtract the ky e to the 4x and from both sides and add 2. And then on the left-hand side, those two terms have a y in common, so I'm going to factor it out. So I'd have y times 1 minus k e to the 4x. And on the other side, they have a 2 in common. I can factor that out. And can have k e to the 4x plus 1. So now I can get the explicit solution, assuming we were able to leave off absolute values. Okay, so I'd have y equals 2 times k e to the 4x plus 1 over 1 minus k e to the 4x. And the initial condition was y of 0 equals -2. And remember, our earlier solution was undefined here. Or the earlier form of the solution was undefined. For y equals -2. Okay, if we look at this form, so the y is -2 and x is 0, right? So then we'd have e to the 0, which is 1. So I'd have k plus 1 over 1 minus k. And then think of this as being over 1, and we can cross multiply. I'd have -2 times 1 minus k equals 2 times k plus 1. Let's just go ahead and multiply out. So I have -2 plus 2k equals 2k plus 2. And notice that the 2k's cancel, and we get -2 equals 2, which is clearly a contradiction. -2 is not equal to 2. So we can't get an explicit form for either for k equals -2, and not this way, or for even, for y equals -2, or even for y equals 2, because you can't take the natural log of 0, right? So we would run into trouble even if y were equal to 2. So we're not able to get our form or solutions in this form for y equals plus or minus 2. But then it says, see the direction field on the next page, and think of, we had kind of already talked about this, the y squared minus 4 can be written as y plus 2 times y minus 2. So the critical points where y equals plus or minus 2, right? Which is where you just get those constant solutions. And when we look at the direction field, right, you see like there's this equilibrium solution right here and right here. So if y is equal to -2 for any x value, it's just y equals -2 for all x values. So the solution for this one is y equals -2. So we could have gotten that from the last section, but just for future reference, if you have to find an explicit solution, that's kind of how you go through trying to get the y's isolated. Okay, so that is it for 2.2. So now 2.3. And this is something you also should have covered in your Calc 2 class, but I know for some people that's been a while since Calc 2. So I'm not assuming that you know how to do this. I'm starting kind of from scratch. So first thing we get is a definition. So it says a first order linear differential equation, and we have to actually talk about linear before, is one that can be put into this form where P and Q are continuous functions. When I say continuous functions of X on a given interval. So this is what they're going to call the standard form, and notice you don't want anything in front of dy dx. So this right here is what we're going to call the standard form. So it says when solving these types of equations, we'll usually need to use what's called an integrating factor, and we'll use mu of x, although I think the Calculus 2 book called it I of x, I for integrating. So it says when we multiply both sides of the equation by mu of x, the differential equation, the left-hand side of the differential equation looks like that. The dy dx is the same as y prime, right? So all I'm doing is multiplying through by mu. So mu y prime plus mu times y, and then we'd have equals mu times q. I'm just focusing on the left-hand side. But if we have this, mu times y prime plus, oops, why do I have mu prime? We don't have that. When we multiply both sides of the equation by mu of x, if I just multiply by mu of x, it wouldn't look like that. We would just get mu y prime plus mu py. I don't know what happened to the p. Equals mu q. Yeah, if this is true, this is what we have, just multiplying. We'll usually multiply both sides of the equation by mu of x. When we do that, the differential equation won't. Hang on one second. So u must satisfy the property. I don't have my book with me. So I'm going to come back to this on Thursday. For now, there is a way to get the left-hand side to look like this. Mu y prime plus mu prime y. There is a way to do that. I just have to think about that for a minute. I'll come back with that on Thursday. But suppose then we do have this. So if mu y prime is equal to mu prime, or plus, if the plus mu prime y is the left-hand side, this is the product rule applied to mu times y. Right? If we had mu times y and we want to take the derivative, right? We do the first times the derivative of the second plus the second times the derivative of the first. I think the key is we just want to find an integrating factor so that the left-hand side is that, not we don't multiply by. So I think we want the integrating factor. To fit left-hand side, I'm just gonna abbreviate left-hand side, LHS equals mu y prime plus mu prime y. So we want to find some function that when we multiply both sides of the equation by mu, the left-hand side of the equation does look like this. So then comparing those two left-hand sides to one another, the mu y primes already match up. We need then these two to be equal to each other. The first terms already are equal. This is what we need. We need mu p y to equal mu prime y. And then we can just divide both sides. So if we have mu p y equals mu prime y, we can divide both sides by y, assuming y is not 0. Which would give us mu p equals mu prime, or I'm just going to switch sides, mu prime equals mu p. And it says now we can treat that as a separable differential equation and solve for u. So I'm just going to multiply or divide both sides by mu. So we have mu prime over mu equals p. And then we're going to integrate both sides with respect to x. So what about mu prime over mu? What's that going to give us? Think of du over u, right? Mu prime is just the derivative. So if we had du over u, right, natural log. So we're going to have natural log of mu, and technically we should use absolute value, but we're almost never going to use absolute values when we're actually solving the problem.
Wait.
Okay, so mu is some function, right? So say I let u be the whole denominator. Then I have to find du. So du would be the derivative of that, and then we'd have our dx at the end, right? Mu is some function of x.
I think the mu's and everything are really good.
Yeah. So you don't ever have to go through the derivation of this. So I won't ever have you do this. I'm just kind of deriving the process.
Right.
So here it's like if I did a u substitution, u would be mu and then du would be its derivative, which would be this. So I'd have du over u, right? And so I'd have ln of u, but u is u.
Yeah.
Yeah.
So,
but then we don't know what p is. P is some function of x. So we're just leaving that as the antiderivative of p dx. And then to solve for mu, we're going to exponentiate both sides. And this is where we're pretty much never going to use the absolute value. So we're just going to say mu is e to the antiderivative of p dx. So this is what you guys need to know. I don't know if I put this on the syllabus, but on our exams, I let you bring in a 4x6 note card one side.
this one's,
Yeah.
wow, that's crazy.
In other classes, I give the formula sheet, but this one you get to make your own note card. So this is definitely something that you would want to put on your note card, the formula for the integrating factor. And so we'll see how, once we calculate this mu and then multiply both sides by mu, how that helps us solve the differential equation. The next page is all about transient terms, which I'll talk about, but I think after we do an example. Like I want us to see how this works. Okay, so we just want to remind ourselves that if it's linear, mu equals e to the antiderivative of p dx, and then we multiply both sides of the DE by mu. And I'm going to generally put it in standard form, which means we don't want anything in front of dy dx. Okay, so for this problem 4, oh, wow. The standard form, since I don't want anything in front of dy dx, I'm going to multiply everything by 1 over x or divide by x. So I get dy dx plus 2 over x times y equals 3 over x. The p of x is what's in front of y. And we don't really ever use the q, but the q is what's on the right-hand side. And mu is e to the antiderivative of p. So and here's the thing, is we just need to find a function that works. So when we do this, the integrating, the pdx, this part, we don't need to add a constant, okay? So you don't need a constant of integration because we just want to find a function that works. If you do a plus c, that gives you all the functions that work. If we just want one, why don't we use the easiest one, where c equals 0? So don't need a constant of integration. Okay, so back to our problem. So what's the antiderivative of 2 over x? 2 ln x. And we're going to leave off the absolute value. The only time that I would put the absolute value on is if they gave me an initial condition where the x was negative. Then we have to use it because you can't take the log of a negative number. Then we want to see if we can simplify this. Can we simplify that? Yeah. And this is the tricky part. What does it simplify to?
X squared.
X squared, right? Because you need the e and the ln right next to each other to like cancel them. So you can't have that 2 there. But there's that property of logs that says if you have ln of a to the k, that's k ln of a. So you can bring the exponent down in front. Our exponent already is down in front. So we're going to put it back up. So e to the ln x squared, and then we get x squared. So now what we want to do is multiply both sides of the DE by x squared. And when I say DE, what I mean is the DE that was in standard form. And here was our standard form. So if I multiply through by x squared, I get x squared dy dx plus, okay, so x squared times 2 over x becomes 2xy equals, and then 3 over x times x squared becomes 3x. If we've done everything right, the left-hand side, now remember, should be mu times y, the whole thing prime. So mu was 2x squared y prime. Let's just check and make sure if that's right. And all we have to do is use the product rule, right? Not 2, I don't know where that 2 came from. Just x squared y. So let's make sure that when we apply the product rule, we get this back. So first times derivative of the second, yep, first derivative of the second, plus the second times the derivative of the first, yep, second derivative of the first. So the left-hand side is x squared y, whole thing prime. The right-hand side still stays the same. Remember, we want to solve for y, but that y is like part of a derivative, so all we have to do is integrate both sides. So we're going to take the antiderivative of both sides. What about the antiderivative of a derivative? Yeah, so we just get x squared y equals, and then the antiderivative of 3x. Three over 2x squared, and then we'll put our plus c here. And then here we can get our explicit solution by dividing through by x squared. So explicit solution. So y equals, so if I divide that by x squared, the x squareds just cancel. So I get 3/2 plus c over x squared. Okay, so I'm going to go back and look at the previous page and talk about so it says the method of solution first, write the differential equation in standard form where there's nothing in front of dy dx. Then whatever is in front of the y is your p of x, and the left-hand side, or the right-hand side is your q of x. 2 says find the integrating factor. So the integrating factor is mu equals e to the antiderivative of p dx. And again, where we don't need to use the integrating factor when we, or the constant of integration when we do that antiderivative. And then once you find the integrating factor, multiply both sides of the differential equation by that integrating factor. Then the left-hand side should be the derivative of a product, and it should always be the derivative of mu times y. And then you just integrate both sides because the antiderivative of a derivative, those processes cancel out. And you'll just get mu times y, and then you'll be able to solve for y. Okay, so it says the example that the text did and the discussion of transient terms. So it says, suppose that this is our differential equation. It's already in standard form because there's nothing in front of dy dx. And then our p is whatever in front of y. So here the p is just 1. And so mu is e to the antiderivative of 1. And the antiderivative of 1 is just x. So the integrating factor is e to the x. So it says, show that when we multiply both sides by e to the x, we have the derivative of a product on the left-hand side. So we get, I'm going to do it up here. So I'd have e to the x dy dx plus e to the x times y equals x e to the x. And then the left-hand side, I want it to be mu y prime, but mu is e to the x, y, and then the whole thing prime. And if I apply the product rule to that, here's first times derivative of the second plus the second, and then the derivative of the first. Well, if the first is e to the x, its derivative is also e to the x. So the left-hand side is just e to the xy, whole thing prime. And then we do the antiderivative of both sides. And then on the left-hand side, we'd get e to the xy, or y e to the x. And on the right-hand side, we'd use integration by parts, and we'd get this. And then we can solve for y by dividing by e to the x. And so in the first term, the e to the x would cancel, and we just have the x. In the second term, e to the x over e to the x is 1, and then plus c over e to the x, which is the same as c e to the negative x. So this is the general solution. And then as x gets really large, e to the negative x goes to 0. And that's what's, if you have any terms that go to 0, those are called transient terms. So it says, consider the solution curves for different values of C. Which one corresponds to C equals 0? So C equals 0, right? You just have y equals x minus 1. Well, what does the graph of that look like? Yeah, it's a line with slope 1, y-intercept -1. Right? So C equals 0 is just the one that's a straight line. Right? The slope 1. And then the other ones correspond to different values of C, but you see that as x gets large, all of the other solutions kind of converge to that solution since the exponential term becomes negligible as x gets large. So they all approach that as x goes to infinity. Okay. So let's look at problem 14. Okay, the first thing I would want to do is get it into standard form. So I definitely want dy dx. I'm just going to go ahead and do that right now. Dx, that's gone, equals 0. And then I want the dy dx and the y on one side, everything else on the other. So I want to keep these terms for now on the left-hand side of the equation, and I'm going to move over the x cubed and the x. So 1 plus x squared dy dx plus xy equals negative x cubed minus x. But then now I don't want anything in front of dy dx, so I'm going to divide everything by 1 plus x squared. So dy dx plus x over 1 plus x squared y equals, so here I'm going to factor out a negative x, and what I'm left with is x squared plus 1, and I'm dividing by 1 plus x squared, so x squared plus 1, 1 plus x squared, those are the same, they cancel. So the p is what's important, and that's what's in front of y. So here's our p, and our integrating factor mu is e to the antiderivative of that. How are we going to integrate that? That's a u substitution. So I would let u equal the denominator, 1 plus x squared. Then du would be 2x dx, and we have x dx, so 1/2 du equals x dx. So mu equals e to the antiderivative. So x dx is 1/2 du. I'll put the 1/2 in front. And then I just have 1 over u du. So I get e to the 1/2, and then antiderivative of 1 over u is ln of u. And here I really don't need the absolute value because 1 plus x squared would never be negative anyway. What is that going to simplify to? U to the 1/2, right? So the 1/2 goes up in the exponent, and then the e and the natural log cancel each other out. So u to the 1/2, which you can write as 1 plus x squared to the 1/2, or you can write that as square root of 1 plus x squared. And then this was our dE in standard form. I'm just going to stop it at the negative x because those other terms cancel out. And I have to multiply through by u. Or by mu. So I'd have 1 plus x squared to the 1/2 dy dx plus, okay, so what about that second term? When I do 1 plus x squared to the 1/2 times this. The x stays, right?
You're gonna get that positive 1/2 on the top. Or you're gonna get that to the 1/2 on the top.
On the bottom, right? So I would have, this would be on the top, but then in the bottom, it's to the 1, right? So it's like I have, if I have 1 plus x squared to the 1/2 over 1 plus x squared, right? Just think of if I asked you to simplify w to the 1/2 over w, right? We just subtract exponents. So you could either write it as x times 1 plus x squared to the negative 1/2 or x over 1 plus x squared to the 1/2, either way. And then equals negative x times 1 plus x squared to the 1/2. Now remember, after we've multiplied both sides by mu, we should have the product rule on the left-hand side. So this should be mu y whole thing prime. Mu is 1 plus x squared to the 1/2 y prime. I'm going to check before I go on, but that should be the case. So think first times derivative of the second times derivative of the second plus the second and then the derivative of the first. So think about taking the derivative of the first. So the 1/2 would come out in front, 1 plus x squared to the negative 1/2, which puts it down into the denominator, times the derivative of what's inside, which would be 2x. So the 1/2 and the 2 cancel, and we just have the x left, right? So this, the left-hand side is the derivative of this product. Okay? And now we just integrate both sides with respect to x. So the left-hand side, antiderivative of a derivative, those two things kind of cancel each other out. And we get 1 plus x squared to the 1/2 y equals the antiderivative of the right-hand side, and we would do a u substitution just like we did above. So the x dx gets replaced by 1/2 du. I'm going to bring the negative out in front. And then this is u. So I have u to the 1/2. Okay, so the negative 1/2 is a constant that stays out in front. What's the new power of u? 3/2. And so then we'll have a 2/3 out in front plus c. So the 2's cancel. And so I have 1 plus x squared to the 1/2 y equals negative 1/3. U is 1 plus x squared to the 3/2 plus c. And then we can get the explicit solution by dividing every term by 1 plus x squared to the 1/2 or multiplying by 1 plus x squared to the negative 1/2. So I'd get y equals negative 1/3. And what about 1 plus x squared to the 3/2 divided by 1 plus x squared to the 1/2? Yeah, just to the first power. So just 1 plus x squared. And then plus c. You can write c over this, or you can write c times 1 plus x squared to the negative 1/2.
we'll have to see for this facility.
Yeah,
Can you go back up a little?
yep.
I'm trying to keep up because you have a delay.
Oh, yeah,
And so you're
Okay.
talking ahead and then I'm looking up and
Yep.
it's just a little delayed.
yep.
I was going to say,
How is this line the same as this line?
No. So one step above, if you divide it by 1 plus x squared to the half.
Mm-hmm.
So you're saying I can write that bottom line as all of that, but just c instead of c times 1 plus x squared to the negative half?
No, you could write it as c over 1 plus x squared to the 1/2.
But you have to have the,
Yeah, you can't just have the c by itself. Okay, a discontinuous right-hand side. So later, much later in the semester, we're gonna look a lot more at right-hand sides that are discontinuous. A common application is with electrical circuits. They kind of aren't off or on. And so a lot of times we'll have this function that is 0 for up to a certain time, and then the switch gets turned on and then it's at 1. Or maybe it's on and then at a certain point it gets turned off and jumps down to 0.
Semiconductors, you mean? Or, I don't know. I just assume semiconductors are involved somehow because that's
It's possible.
not.
Okay, so we want to find a continuous solution satisfying that differential equation, and we're also in this problem given an initial condition. So here I say 3 solutions are shown, and then it says, is the solution corresponding to our initial condition shown? And is it? Is one of those 3 solutions the one we're looking for? Yeah, because our initial condition is y of 0 equals 1, and that's right here. Right? So that the one in the middle is going to be our solution. So it says, does the direction field seem to indicate the solution contains a transient term? So if there's a transient term, that means as x goes to infinity, that transient term goes to 0. So it really, it's almost like there's really only one solution where that c e to the whatever goes to 0. Does it seem like they're all converging towards the same solution? Yeah. Okay. So what we're going to do is we're first going to just solve the differential equation for the top part. We're going to solve it on 0, 1. So first we'll solve on the interval 0, 1. It's already in standard form, right? What's our p of x? Is just 1, right? And then here, then the right-hand side, or the q, would also just be 1, because when x is between 0 and 1, the right-hand side is just 1. So our integrating factor is mu equals e to the antiderivative of p dx. But p is just 1, so we'd have e to the antiderivative of 1 dx, and the antiderivative of 1 is just x. So we just get e to the x. And so I'm going to multiply by e to the x. And so I'd get e to the x dy dx plus e to the x times y equals e to the x times 1, or just e to the x. After we multiply by the integrating factor, the left-hand side should be the derivative of mu, which is e to the x times y. I always check before I go on. So if I apply the product rule to e to the xy, first times, derivative of the second plus the second, which is y, and the derivative of e to the x is e to the x. So that's correct. And so now that I know the left-hand side is a derivative, we can integrate both sides. So what do I get on the left side? E to the xy, right? Antiderivative of a derivative. Just get what's inside parentheses. And then on the right-hand side, the antiderivative of e to the x plus c. And then so our explicit solution, I'm going to divide by e to the x. And so I'd get y equals, well, e to the x divided by e to the x is 1 plus c e to the negative x, or c over, I'm going to call this c1 actually, because we're going to have to go through a similar process for x greater than 1, and we'll have a new constant of integration. Our initial condition is y of 0 equals 1. So the y is 1, the x is 0. But e to the 0 is 1. So what does C1 have to be? 0. So on the interval 0, 1, y is just the constant function 1, which matches what we see in the solution I produced with Maple. Okay, now we're going to do the same thing for x greater than 1. The p is still 1, but now the right-hand side is negative 1. Right? So f of x for x greater than 1 is negative 1. So for x greater than 1, we still have p equals 1, but q equals negative 1. So our integrating factor is the same because our p is the same. So our differential equation becomes e to the x dy dx plus e to the x y. And this time it would just be negative 1 times e to the x. We already know that the left-hand side is the derivative of a product, e to the xy prime equals negative e to the x. I think the whole next page is, well, for me it's blank. I'm not sure if it's blank for you guys. No, okay. So we integrate both sides, and here we get e to the xy, and on the other side we just get negative e to the x plus c, 2. And then I would divide by e to the x, just like we did before. So I get y equals negative 1 plus c2 e to the negative x, or c2 over e to the x. I'm just going to write c2 e to the negative x. But we still want to solve for c2. And we can't use the y of 0 equals 1, because we can only use x's greater than 1. But this is where the fact that we're trying to find a continuous solution comes into play. So I'm going to kind of have to continue over here. So what did I have? Y equals negative 1 plus c2 e to the negative x. To be continuous, Usually I'd need to use limits because here it has x strictly greater than 1. So I'd have to take the limit as x goes to 1, right? The place where this has a discontinuity is at x equals 1. I'm just going to say, we would actually need the limit to be equal to the function value, right? We'd need this part of the solution to match up with this part of the solution right at x equals 1. When we plug in x equals 1, we should get y equals what? Equals what? 1, right? Because this is, so far, what we have for our solution is right here. Now we're going to make a new piece, a new piece that is starting at x equals 1 and going to infinity. So at x equals 1, it has to pick up right where the other piece left off, which was the constant function, right? So when x equals 1, I have to meet up with the other piece of the solution I already found. So let's plug 1 in for x and 1 in for y, and that's going to help us solve for C2. So 1 equals -1 plus C2 e to the -1. So first I'd add 1 to both sides, so I get 2 equals C2 e to the -1, e to the 1, e to the -1. I don't know where that shouldn't be a negative, I'm sorry. You can always correct me if you see that I make a mistake. This was just e to the x, right? It was never an e to the -x.
Yeah, when you divide it.
Yeah, no.
Oh, it was, okay.
Wait.
Yeah, it's right, yeah. When we divide by e to the x, yep, that is e to the -x. Okay, so no, that's right. So e to the -1 is right. So 2 equals C2 e to the -1, which is the same as 1 over e. So to solve for C2, we'd multiply both sides by e. So we get 2e equals C2. I'm going to write the entire solution up in the top margin as soon as people get caught
I
up.
want it to be 2 over e.
Well, this already, e to the -1 is over e, right? And so then to get the C2 by itself, then I'd multiply both sides by e. Does that make sense?
Yeah.
Okay. So our continuous solution is y equals, it's just the constant function 1 if x is between 0 and 1. And it's -1 plus C2 was 2e, e to the -x for x greater than 1. I probably wouldn't write it like that. I would write this as 2e to the -x plus 1. Just using law of exponents, e to the first times e to the -x, you can add exponents. All right, so that is it for 2.3, which again, you should have seen in your Calculus 2 class, but 2.4, this is not something that's usually covered in Calc 2. But for people who have taken Calc 3, this is gonna look very familiar. Exact differential equations. So it says, suppose we had the differential equation y dx plus x dy equals 0. We could divide everything through by dx, and then we just have the y there plus x dy dx equals 0. And it says, and note that the left-hand side shows the product rule. So similar to what we did in the last section. If I looked at x times y and took the derivative, right, we'd get first, which is x, times the derivative of the second, which is dy dx, plus the second, which is y, times the derivative of the first, which is just 1. So we'd have x, y, the whole thing prime equals 0, and then we just integrate both sides with respect to x. And then what do we get on the left-hand side? xy. And what do we get on the right-hand side? Constant. Or y equals c over x is fine too. Either of those. So it says in Calc 3, it is shown that if z is the dependent variable, and we're looking at z as a function of x and y, where x and y are two independent variables, and we looked at partial derivatives on the first day of class. So if you take the partial of f, this function with respect to x, that's when you treat y as a constant, and then multiply by dx, plus the partial with respect to y, dy, that's equal to 0. Oh, here, if f of xy is a constant. Okay, so first of all, the differential of z, so if you've taken Calc 3, right, this should look familiar. Z is a function of x and y. And you can think of, well, x is just x, y is just y. And then you use the chain rule to take the derivative. We got that differential. You don't need to know that. If you took Calc 3, that should look familiar. So if f of xy is equal to some constant, and we take the derivative of both sides of this equation, so the whole equation, we know that the derivative of the left-hand side is this, and then the derivative of a constant is 0. So it says, in other words, given a family of curves, f of xy equals c. So if we just have a constant on the other side, and on the left-hand side we have only x and y, so you have a whole equation with only x, y, and constant, then you can get the graph in 2 dimensions. It's not in 3 dimensions anymore. If you didn't have that equals c, then it's a graph in 3 dimensions. But when you set it equal to a constant, it's what's called a level curve. So it says we can generate a first order differential equation by computing the total differential. The total differential is this part right there. So it says example of a family of curves. So like here, x squared plus y squared equals c. What does the family look like? So if c equals 1, what does that curve look like? Circle of radius 1 centered at the origin. What if c equals 4? Circle of radius 2 centered at the origin, right? So this equation gives a family of curves. They're all circles centered at the origin, right, with different radius. So what does the family look like? Concentric circles centered at the origin. So it says a differential expression. So this is not an equation anymore because there's no equal sign in there. They just have an expression. So there's some function of x and y in front of dx and some function of x and y in front of dy. In Calc 3, this was our p and our q. Our p dx plus q dy is an exact differential in a region R of the xy plane if it corresponds to the total differential of some function f of xy. So they're going to give us like this expression. Our goal is to figure out, okay, what's the original function it came from? So it says a differential equation in this form. This is really important, that it's equal to 0. is said to be an exact equation if the expression on the left side is an exact differential. And we'll see how to determine whether or not it's an exact differential. So it says in Calc 3, this idea was used, or for those of you taking Calc 3, this will come a bit later. We used this idea when we were seeing whether a vector field was conservative or not. We checked, does partial of P with respect to Y equal partial of Q with respect to X? If those two were equal, it was conservative, and we can maybe apply Green's theorem. So it says the following theorem is a test to see if something is an exact differential. So notice that the M is what's in front of the dx. You always take the derivative with respect to the other variable. So the M is already with dx, so you take its derivative with respect to y. The N is already with the dy, and so you take its derivative with respect to x. If those two partial derivatives are equal to one another, then it's an exact differential. We want the M and N to be continuous and have continuous first partials. Pretty much everything will be given is continuous. Okay, so this is the thing you want to focus on. So like when you're making your note card, that's what you want to put on your note card. For solving a differential equation, you probably want to make note of what the standard form is. And then this is the equation you check to see if it's exact. Okay, so we're gonna look at these steps as we do problems 2 and 4. So if the equation is in the standard form already, where you have the dx and with a function in front of it, and then a dy with a function in front of it, and the whole thing is equal to 0, which is the case here. We have something in front of dx. This we have minus, that's okay. Then the n will just bring the minus along with it. In front of dy equals 0. So this is our m. This is our n. So the m is already in front of the dx. So what we want to do is check m's derivative with respect to the other variable, with respect to y. So remember, when we take the derivative with respect to y, x is a constant. So what will the derivative of 2x plus y be? Just 1, right? If x is a constant, the derivative of 2x is 0, and then the derivative of y would be 1. And then n is already with the dy, so we check the partial with respect to x. So what's the derivative of that expression with respect to x? -1. So these are not equal, so it's not exact. Okay, so let's check the next one. It's already in standard form. There's a function in front of dx, that's our m. And our function in front of dy, that's our n. The first thing we do is check the partial. So m is already with the dx. Take the partial of m with respect to y, which means we're treating x as a constant. So what's the derivative of sine y? Cosine y minus just sine x, right? Because the derivative of y is 1, and the sine x is just a constant that stays there. And then we'll check the partial of n with respect to x. So what's the derivative of cosine x? Negative sine x plus cosine y, because cosine y is a constant, the derivative of x is 1. And what's the derivative of minus y? 0. Yep. So I just get this, and yep, they're equal to one another. So it's exact. Okay, and it says if it is exact, we're supposed to solve. So let's go and look at step 2. So now we're assuming that if we compare it to, since it's exact, we know the left-hand side is the total differential of some function f. So what's in front of the dx is the partial of the original function with respect to x. So we know that the partial of f with respect to x is m. So sine y minus y sine x. And the partial of f with respect to y is n. We're trying to get back to the original function f. We know two of the derivatives, the derivative with respect to x and the derivative with respect to y. So if we know a derivative and we want to get back to the original, what are we going to have to do? Integrate, right? And you can choose either one. Just choose the one that looks easier. If we integrate the first one, what are we going to integrate with respect to? X, right? If it's the derivative with respect to x, we have to integrate with respect to x. If we integrate the second one, we have to integrate with respect to y because it's the derivative with respect to y. So which one do you want to do? The first one or the second one? I do the first one, it just has fewer terms. I'm just going to do it on the next page. Okay. So f of xy is the antiderivative. Okay, I'll refocus. First of all, I'm just copying what we had on the last page. So sine y minus y sine x. Dx. Okay, I'll refocus. Okay, when we integrate, it's the same as when we're doing partial derivatives. So when I'm integrating this function of x and y with respect to x, all the y's are, I think of them as constants. So what would the antiderivative of sine y be? X sine y. And then minus y is a constant that just stays there. And what's the antiderivative of sine x? Is it positive cosine or negative cosine?
Well, it'll be positive.
It'll be, right, it's right. This will turn into positive. Okay, and I'm not done yet, but so just to check quick, if I took this derivative, y is a constant, the derivative of cosine is negative sine. Okay, now normally we would write plus c, right? We get a constant of integration. But when we integrate with respect to x, remember we're treating y as a constant. So we don't just get plus c, we get plus, you can call it like g of y or h of y. That constant of integration might actually involve y. So now once we get that done, so we've used m, right? I haven't used n yet. So what I want to do is we just integrated with respect to x. So now differentiate the answer we just got with respect to y and compare to n, right? Because n is supposed to equal. I'm going to zoom out if I can just a little bit here. No, it won't let me do it as I'm recording. Okay. Okay, so if this is our function, then I get partial of f with respect to y. So now we're back to treating x as a constant, right? So when I take the derivative of x sine y, x is a constant that stays in front, and what's the derivative of sine y? Yep, just positive cosine y. plus what? Cosine x, because that's the constant and the derivative of y is 1, plus g prime of y. And now I'm going to compare it to n. Most of the terms should match up, okay? So our n from the previous page was cosine x plus x cosine y minus y. So if I put those two together and compare, I see, okay, the cosine x's match up, the x cosine y's match up, so what's left for g prime of y is negative y. So if g prime of y is negative y, then what's g of y? Negative y squared over 2 or negative 1/2 y squared. And you can do a plus c if you want, but we're already setting it equal to a constant on the right-hand side. Remember, what we were doing was looking for this f of x, y equals a constant. So if you want to add a c here, that's fine, but we're going to combine all of the constants over on the right-hand side. So our solution, and these are almost always going to be implicit solutions. So we start where we first found our f of x, y. The only thing I wasn't sure of was the g of y. And now we know what the g of y is. So I'm just going to use this to update the solution I had before. Everything else stays the same. So x sine y plus y cosine x minus 1/2 y squared equals c. If they had given us an initial condition, I don't think they did, I'll go back and look. But then we would just do it how we did it before. Whatever the x value is, plug that in. Whatever the y value is, plug that in, and then solve for c. They didn't give us an initial condition. Okay, so it's 3:30. I think I'm going to stop there and have you do group work.